In this video, we're going to start a unit on frames and machines. We already looked at trusses, and trusses are multi-membered structures where every member is a two-force member. But a frame or a machine is a multi-membered structure where the members, some of them can be two-force, but many of them are what we call multi-force members. And I'll explain that to you more in this example of what a multi-force member is. A machine is similar to a frame in that you've got elements that are multi-force members, you've got elements that are two-force members, but a machine is basically designed to move. It's designed to transmit loads, to transmit energy, to move in some way. It's a tool, it's a lift, it's a tractor. It's designed to move, as opposed to a frame which appeals to a civil engineer, which basically remains still. So we're going to work a number of frame problems and a number of machine problems to just illustrate how you work the problems. Furthermore, we already did two-dimensional rigid body equilibrium. And when we did 2D rigid body equilibrium, we drew free body diagrams, we looked for two-force members, we inspected support reactions, and pretty much all of those skills we're doing here for frames and machines. But again, we're typically a 2D rigid body equilibrium problem was like one member with some support reactions. A typical frame is going to have multiple members. And so that's kind of the difference. So this is a very simple frame, and really you could call this a 2D equilibrium problem. But this is from the Hibbler's book. It's a preliminary problem. You've got a horizontal member A, B, D. You've got an angled shape member BC. We have a cable that's tied off at the ground, and that cable comes up around this pulley and over, and there's a 400 Newton force applied to that cable. We want to find the reactions at A, B, C, and D. When you look at this problem as is, it's, how do I solve it? How do I solve it? But you draw the free body diagrams, then you have a problem that you can solve. And so students sometimes try to get by without drawing a free body diagram, but it's super important that you draw a free body. So let's start with this horizontal member here. So you've got a pin here, so I'll put a couple pin reactions on him. Since this force is going to the right, I drew AX to the left. I'll explain AY in a moment, why I drew that down. I need a force at B. And so at B, you could put two forces in. You could put a BX and a BY. But BC is actually a two-force member. So what is a two-force member? So remember a two-force member. So a two-force member basically has forces applied at 2 points on the body. So in other words, it has a force at this end and a force at this end and nothing else. There's no other load, there's no other couple, there's no weight of the member. It's only applied at 2 places. And if you have a member, you have an arbitrary member that looks like this, there's a point A and a point B. And if we draw a straight line between these 2 points, we call this X prime and we call this Y prime. If I put an AY prime and an AX here, and if I put a BY prime and a BX here, where the X prime axis is along a line that's a straight line that's drawn between these 2 pins. And if there's no other force acting on this guy, no couple, no force, no weight, so the only forces acting on this member are at the 2 ends, at 2 points. Well, if you look at this guy, and if you sum moments about B, AY has to be 0 if there's no other force. If you sum moments but A, there's no other force, no other couple, then this By, or By prime, has to be 0. And so you're basically left with a member with forces applied at one end, at 2 points on it, where basically the forces have to act either, they have to act along a line drawn between the two pins. And either along that line this guy is in tension, or along that line this guy is in compression. But the point is there's a single force that acts along this member. That's a two-force member. So when you look at this problem, you should immediately recognize BC as a two-force member. If you do, then you can draw a line from C to B, and this is 1.5 meters up, 2 meters this way, so that's a 3, 4, 5 slope, and we could draw a single force FBC acting along this slope, and which makes this problem easier. If you don't recognize this guy as a two-force member, and you put a BX and a BY here, and then you end up with a CX and a CY here, you can actually still solve the frame or solve the structure, but you've just made the job harder. And so like everything else, if you're intelligent, you know what you're doing, you can make life easier on yourself. So this is a two-force member, and so he's applying there. But look at this horizontal member. He's got forces applied here, here, and basically at this pin, something like this. So this is basically, this is what you'd call a three-force member. 1, 2, 3, at those guys. And so if you look at him, this A resolves into a FA. You've got FBC, and then you get these forces. And actually, these guys are going to intersect somewhere. This is a three-force member. And so a three-force member has got forces applied at 3 points. In the line of action, if you add AX and AY together to get a FA, if you've got FBC, and you add these guys together to get a pin reaction here, and this is D, so this is FD. The line of action of these three forces intersect. And so that's a property of a three-force member. We hardly ever talk about it in statics, and we almost never use it. But there's actually a few rare problems, interesting problems, that are hard to understand. It's like, why is that guy in equilibrium? Without being able to draw it as a three-force member. And maybe in a later video we'll talk about three-force members more. But my point is, this is a two-force member. This is a three-force member. Later, we're going to work a frame that's got like pins applied at 4 locations on it. So that's a 4-force member. And so again, a frame is made up of a number of members, some of which might be 2-force, but some are also multi-force members. And that's basically what's going on here. So we have a free body diagram of ABD. We have the 2-force member. Okay, so let's talk about this pulley. So we talked about the 2-force member. We've got the single force there. So this pulley. So when I'm drawing a free body diagram, I cut this cable, and I cut this cable. And I basically, there's a 400 Newton force in this cable here and here. And so I can leave those forces on the pulley just like that. And I can work the problem that way, leaving those forces on the pulley. But if you're this pin right here, you don't know that these forces exist. If you're this pin or you're this frame, all you know are the pin reactions. So if you draw a free body diagram of just this pulley, so that's this picture right here. You draw a free body diagram with a pulley. You got this 400 Newton force this way, this 400 Newton force that way. So what are the pin reactions on this guy? So the pin exerts reactions onto this pulley, a 400 up to oppose this guy, and a 400 to the left to oppose this guy. So if you're this horizontal member ABD, you don't feel these cables. You don't know that there's cables there. All you know is what's on that pin. And so you can leave these forces on the pulley, but you can also put the pin reactions at D. And so the pin reactions at D are these. So these are the pin reactions. And putting these 400 guys at the pins make this just slightly easier than leaving them here, which you'll see. Notice one more thing that we're going to talk about as we work on frames is that these pin reactions act this way on the pulley, but when I drew them here, they act equal and opposite. So the pin exerts forces onto the member, and the member exerts forces onto the pin, and those are equal and opposite. So one of our fundamentals of frames is when we take a frame apart and we represent these two pin reactions, they're equal and opposite. Okay, one more thing I skipped over. So why did I draw AY down? Well, the reason I drew AY down is I like to think about these pin reactions as I work the problem, and I like to get them in the correct sense if I can. Some problems it's hard to intuit the correct sense, but sometimes it is. So in this particular problem, before you leap into drawing AY vertically, what you can do is think about putting a pivot at B and taking moments about B. If you take moments about B, you know that this 400 is acting down, which is going to make this guy pivot clockwise around B. So AY actually has to act down to keep this guy in equilibrium. And so I realized that when I was working this problem. So stop and as you think about the reactions at each of these, stop and think about what possibly is the correct direction. So AY actually should be down. So let's write the equations for ABD. If we leave the forces on the pulley, if we sum moments about A, and we take clockwise to be positive, we have this 400 times 0.2 positive, plus this 400, and so it's 4 meters all the way to the pin, and it's minus 0.2, the radius of this pin. So this 400 is 0.2 closer to A. And so the moment arm of this 400 is 4 minus 0.2. So 400 times 4 minus 0.2. And then the upward component of this guy is 3/5 of FBC, and his moment arm is 2 around A. And we can solve for FBC as 1.33 kilonewtons, and of course he acts at a 345 slope. But notice what happens to this equation if you look at these two 400 terms. You have a 400 times 0.2 term here, and then you have a minus 0.2 400 in this term here. Well, those two terms cancel one another out, and you're left with just a 400 times 4 term. When we go to this guy and take the moments about A, if we take clockwise to be positive, like we did here, then we have 400 times 4 minus 3/5 of FBC times 2. And so we end up with the same equation. So the final story is, if you can, if you cut both of these cables to draw this free body diagram, you can locate both of these forces at the pin. We'll work on another example later of a frame that's got like a vertical member that comes up and a pulley over here and a weight that comes off of here. And we'll draw a free body diagram of the entire frame where we basically cut this guy and we'll put a force out here at the edge of the pulley. But this side of the pulley, this side of the cable, because we did not cut it to make the overall free body, we have to leave him uncut. And we just have a single force out here. But once we separate this pulley, once we take this frame apart, once we draw this guy, and this guy, then when we take them apart, then we can cut the cable and put them here or here on this horizontal member. And then we have the vertical member, cable, reactions, and so on. So if we cut the cable, put a force there. If we don't cut the cable to make the free body diagram, then you have to leave the cable uncut. It's one of our rules of frames. So this is FBC. If you sum moments about B, this is 2 meters, this is 2 meters, this is 400, then you could just tell by inspection that AY is also going to be 400 down. And then finally, to sum forces in the X direction, if you take to the right to be positive, you have a negative AX plus 4/5 of FBC plus 400. And you get AX is 1.47 kilonewtons. Fairly simple frame, but there's a lot here, how to deal with pulleys, multi-force member, 2-force member, and so it's a perfect simple frame.